Well, welcome to Rice 101, module number 4. My name's Griffiths Atungulu. I'm the director of the Arkansas Rice Processing Program. I'm an associate professor and agricultural engineer. My area of expertise is in grain processing and post-harvest systems engineering. I'm housed here in the Department of Food Science with the University of Arkansas System Division of Agriculture. In this module number 4, we are going to delve into the aspect of rice drying airflow. And we are going to look at airflow resistance. We are going to describe factors that affect airflow resistance. We are going to talk about airflow resistant measurement techniques, and then airflow rate for drying of rice. We are going to look at aspects like the impact of grain depth on airflow resistance. And then at the end of it, I would like to provide some recommendations on the minimum airflow rate that are required for drying rice of various moisture contents. So what is airflow resistance? In simple terms, this is the opposition to the flow of air in the grains. As you would expect, if you have rice in a bin and you're trying to push air through, it would move completely different from the case where you don't have rice inside that bin. And typically we measure this airflow resistance in static pressures, and we find that expressed in inches of water. It's a very important consideration, especially in the design of grain drying and aeration systems. And the amount of air that you push through the grain will obviously influence its drying rate. And for rice, that's very important because the rate at which that rice dries will influence things like fissure formation, and if that is not done right, it may reduce the market value of that rice because it impacts on the head rice yield. We want to talk about some of the factors that affect airflow resistance. And in simplicity, kind of shown some of these factors here. The packing of the grain, just as the name suggests, if you have grain in a bin, that grain is going to pack itself. It could be loosely packed or it could be tightly packed. And that packing can actually be captured in what we call packing factors. And for loosely packed grains, we would expect the airflow to flow resistance to be lower compared to grains that are tightly packed. And again, that's because the porosity within that bin or that grain mass is different. The other thing that we would expect to change the airflow resistance within grain mass is the moisture content. As we learn in a few slides here to come, when the moisture content is high, compared to when the moisture content is low, the grain would have completely different dimensions. And those changes in dimensions sometimes may change the porosity of that grain within a grain mass. And as that porosity changes, you'd have the constriction to airflow also varying. And so we'd expect with higher moisture content, we would have maybe the grain is loosely packed compared to when it is at lower moisture content, where it tends to tighten up. And when that happens, the constriction to airflow rate obviously is going to be different. Now, the grain depth is a very, very important aspect to consider, especially when we are drying rice, because the higher the grain depth, the more the resistance to airflow would expect, because that air to move has to overcome more friction, and it also has a longer path of travel. And with that, we would expect different airflow resistances to be expressed when we have shallow layers or deeper beds of rice. The other aspect that I would like also to mention, and I will describe this again later in details, is the fine concentrations. When we harvest rice, it comes in our combines. It has to be separated, but there are many chances that we end up having different particles within that grain mass that is not rice. And it runs from dust all the way to leaves and every other thing. All this can be put together as what we call fines, or sometimes we call them chaff. And their concentration within our grain mass plays a very big role in restricting the flow of the air within that grain mass. Then there's the so-called grain mass configuration. As we fill our bins, the grain has a tendency to form a conical shape on the top. And when it forms that conical shape on the top, it may restrict the movement of the grain, especially in that conical section of the bin. We'll describe this a little bit more details figuratively as we go along. Let's talk about grain compaction, and I mentioned this as we talk in the previous slides briefly in passing. So let's think about grain placed in a bin as seen in this figure here. The grain at the bottom is going to be bearing a lot of weight that is coming from the grain on the top. And by so doing, we expect the bulk density of the grain at the bottom to increase relative to the one at the top, just because it has to bear a lot of weight. And so we would expect that increase or change in bulk density also to influence the airflow within that grain mass. So with higher bulk densities, of course, we would expect more constriction, and with lower bulk densities, we would expect the looseness of that grain, making it to have easier pathways for the grain to pass through. And so grain compaction is a very important factor to look at when we are dealing with airflow resistance calculations. Also, in this figure, I introduced a concept called shrinkage due to drying. On the left there, you see the mass or the volume of the grain before drying. When you dry that grain, some of the volume declines because it's losing some moisture, and so the grain shrinks. And as it shrinks, the depth decreases, but also the dimensions of kernels may change. And with those changes, you'd expect the porosity of that grain to also change. And as that porosity changes, that is going to influence the restriction to airflow within that grain mass. Fines, as I mentioned, are typically those material within the grain mass that are not grain. And this could be dust, they could be frog limbs, they could be leaves, they could be anything that is not grain. Most of the time, these fines are smaller in size, and when they tend to be smaller in size, when you fill a grain bin, they tend to accumulate at the central part of that grain bin. When they accumulate at the central part of that grain bin, they influence the air movement within that central portion of the grain bin. And so the typical practice is to core the grain, remove that central part, and move it on the top and spread it so that we can improve the uniformity of air movement within that grain mass. Another approach is to use a spreader. As you fill that grain mass, use a spreader to kind of mix the grain so that you have all the sizes distributed within that grain mass, so that you can make the movement of the air within that grain mass uniform. There are various other techniques that we can employ, like we can start with a cleaner. If you clean the grain, obviously you're going to remove those fines out of the grain, and that therefore improves the uniformity of the air movement within that grain bin. And so this figure is just to show you some of the configurations that we would expect in a typical grain bin. The peaked configuration there is the natural way that you would expect. You can see the conical shape when the rice is filled within the bin, because again that is natural, because rice, just like any other grain, have what we call the angle of repose. It will tend to form that conical shape as we fill the bin. When we remove the rice out of that bin, on the other hand, it also forms another conical shape configuration, but in an inverted manner. And so you can see these shapes obviously are going to influence the movement of the air within this grain mass. Now, in the next slide is a simulation that we have done to kind of map out the airflow patterns within different configurations. You can clearly see that in a peaked configuration, we tend to have more variability in the airflow at the central part and at the conical part of that bin, as well as on the sides of that bin. When we flatten that bin, which is really the recommended practice, we tend to make the movement of air within that bin much more uniform. The central portion as well as the side portions of that bin tend to have less variability in terms of airflow rates. On the other hand, in the inverted bin configuration, you'd see, again, a huge variability in the airflow rates at the central part and as well as the side part and at the section that has formed a conical configuration. Next, I want to describe airflow resistant measurement. And like I mentioned, we measure this in terms of static pressure. which is basically the resistance of airflow through the rice, and it's measured using a manometer, which is a clear plastic or glass U-tube that is partially filled with colored water. This figure here kind of helps capture that graphically. You see on the left there, on the right we see a U-tube that has got water filling it, and then on one end of that, if we connected that to a system to which pressure is being measured, we would expect that liquid to be pushed down because of the pressure that is generated, and you would expect a pressure difference to be established in those two layers. On the other hand, if we did not have pressure system on one end, then we would expect those two levels to be at the same. So we can use this concept to measure the static pressure that is built as the air flows through our grain bin. And so the pressure causes water to move and create a differential between the two water levels in the U-tube, and that static pressure is that difference in water level. And again, as I mentioned, it is measured in inches of water. Now, the static pressure that is established will depend on the grain depth, and it will also depend on the airflow within a bin system. As you can see, as you increase the grain depth, at a fixed airflow, you would expect to see an increase in the static pressure. And again, just like we discussed in the previous slides, that's because the path of travel is high and there's more resistance that air has to overcome, and so that static pressure increases. Now, at a fixed depth, as you increase the airflow, you'd also see an increase in the static pressure. And again, that's because of increased turbulence within that grain bag that causes more friction that results in the need for or an increase in the static pressure. So for instance, if we have a grain that is at a depth of 20 feet and we are pushing in air at 1 cubic feet per bushel, for rice we would expect that to develop a static pressure of about 8.6 inches of water. Now this is important for us to know that it will depend on the grain type. It will also depend on the grain moisture content. So this chart here is established for a standard moisture content of 13% wet basis. If you change that moisture content, you would expect the static pressure values to shift a little bit. Finally, I want to present you the minimum airflow rates for dry rough rice. And this minimum airflow rate is dependent on the moisture content of that rice. On the first column there, you see the initial moisture content of the rice. In the second column, you see the airflow rate indicated in cubic foot per minute per hundredweight grain. And so at lower moisture content, 13 to 15%, we need about 1 to 2 cubic feet per minute per hundredweight. But as we increase that moisture content, or when we harvest that rice at a higher moisture content, there's need to increase the amount of airflow rate that we would put in that grain. So at 22%, which is like the higher end of harvest moisture content, we would need to increase the airflow rate to 12 CFM per hundredweight. And that is very important so that we can rapidly remove that moisture that is in the grain so that we can prevent that grain from quickly deteriorating. In the next modules, we'll cover a little bit more on the static pressure and also look at the delivery of airflow and how that varies depending on different type of fans. And then we'll also look at fan selection requirements for different airflow volumes. And so with that, I want to say thank you very much for listening to this module on airflow resistance, and I look forward to talking to you in the subsequent modules. Thank you very much for listening.